So in this video, we're going to be looking at NoSQL databases like MongoDB and Cassandra and talking about why they exist and how they can scale better than traditional relational databases. There's a lot of differences between relational and non-relational NoSQL databases from a developer standpoint, but the core differences in terms of why these systems were built the way they are often overlooked. So let's dive into the details. So let's take a look at an example schema that we'd want to store in a database. We can think of this example as an e-commerce site. So we have users on our site. Those users can make orders, and those orders can consist of a number of products. We can see from this diagram that a user corresponds to exactly one order, and we can also see that orders and products have a many-to-many relationship. So one product can be used in multiple orders, and one order can consist of multiple products. And furthermore, we also have a quantity associated with the number of products present in a particular order. So this is a pretty simple schema. So let's look at how this corresponds to a relational model that we'd see in a traditional SQL database. So here's just one possible schema that we could have within the relational model. So we can see for our tables, we have users, orders, products, and order products that map orders to products. And we can see by these lines that we have relationships between these tables. So each order has a user ID that corresponds to the user table, and the order product table has an order ID and a product ID that corresponds to orders and products respectively. What's cool about this relational schema here is we can do any query we want efficiently. So we can see all of the orders in a particular product by looking at all of the order products with a specific order ID, and we can see all of the orders that have a particular product in it by filtering this table on product ID. So this is a super useful construct, and we can represent super complex schemas within this model. If you want to learn more about how to convert a logical data model into a relational schema, you should check out our full course on system fundamentals at interviewpen.com. So the relational model was built a long time ago and was based on having a single database node. So this single database node is responsible for holding all of the data in our entire database. And if we have more data, that means we need a bigger server. We can scale servers to have terabytes of data, so this model worked well for a very long time. And within this model, structuring the schema relationally is really nice because we can make any query that we want efficiently. So within the schema that we showed earlier, if we want to get all of the products within an order, we can look at a single order. We can filter down the order product table to get all of the products associated with that order, and then we can use each one of those order product records to get back to a product. And now we can have a list of all of our products associated with that order. And we can also go the other way around if we want. So let's say we want to count the number of orders for a product. We can look at a product, filter down our order product table to a number of order product records, and then find the order for each one of those order product records, and then count them. If all of our data is stored in a single database node and everything is indexed properly so that these joins are efficient, we can do both of these queries perfectly efficiently. And any other query you could imagine doing, you can also perform efficiently within that relational model. This makes schema design really simple because there's often a right answer. For any logical data model, we can come up with a relational schema that is perfectly efficient for any query pattern. And that's really powerful. However, as the internet grew over the years, companies started running into problems where they couldn't actually fit their entire database on a single node like this. There is a limit to the amount of storage that we can put in a single server, so it became necessary to distribute the data across a cluster of servers. This is done using sharding, so we're splitting up our data set and storing it on a number of servers, so each one of the servers only has a subset of the entire data. So with this model, if we have more data, all we have to do is add more servers. And for the most part, we can scale the number of servers we have in a database cluster infinitely. However, having this data distributed across multiple servers introduces a lot of overhead and additional challenges that we have to deal with. So if we think about our relational model, and if we go with a naive solution where each one of our, in this example, 4 database nodes holds a subset of orders and a subset of products, let's look again at the query where we want to get the number of products in an order. We can look at our order. We're looking at one order, so that'll be stored on one of these database nodes. And then we're looking at our order products table. And if we want, we can store our order products in our database such that all of the order products associated with a particular order are stored on that same database node as the order. So all of this data, the order and all of our order products associated with it, can all be stored on one node. However, our products will likely end up on different nodes. Because orders and products have a many-to-many relationship, there's no way within this model for us to be able to store all of the products on the database node that's associated with that order, because then a product would have to be stored on multiple database nodes at once. So if we had a large order consisting of multiple products, we'd have to go out to multiple database nodes, and this would really decrease efficiency. In the same way, if we want to count the number of orders for a product, we have the same issue in reverse. So we can store all of our products and their associated order products within one node, but the orders associated with those order products will be scattered across all of our database nodes. This means that we might need to reach out to a significant number of database nodes in order to get the data that we're looking for. So if we're thinking about how to solve this problem, we'll realize that there's no right answer. We don't have the simplicity of having a single database node where one schema can solve every problem. We instead have to look at our query patterns and store our data according to how the data is going to be queried later. If one of our main query patterns is getting all of the products associated with an order, the only way to do this effectively is to copy the data about the product to every single order. So let's take a look at that case. So now each node, instead of having a subset of orders and a subset of products, now has a subset of orders, and for each order has a copy of the products associated with it. So now when we're getting all the products in an order, all of them will be stored on the same database node because all of these products associated with the order are copied into the same node that order is stored on. This has interesting implications for writes, however. Every time we create an order, we'll have to query the information about the products and then copy it over to the order record. And we'll also notice that it becomes really difficult to update certain pieces of information about a product. Because that product is copied across every single order that the product is used in, we'd have to update that product record in a significant number of places. But if this is one of our main query patterns, we might decide that making our product record immutable and eating the additional storage cost of copying this product to multiple places is worth the trade-off for more scalability. Now, one of our other query patterns that we discussed was counting the number of orders for a product. With our relational model, we were getting all of the order records and then counting them at the end, and this was fine because all of the data was stored on a single node anyway, so it doesn't take a lot of time to do that type of query. However, if our data is sharded, we have to make significant trade-offs like we saw with getting products in order to put these two pieces of data in the same node. But luckily, we're only getting a count. So what we can actually do here is save a count of the number of orders within our product record. So every time we create an order, we now have to go out to every single product that order is in and increment that count. But our query is now super efficient because all we have to do is get the single product record and it has that count already in it. So this again is a trade-off with writing. So creating an order will take more time because it has to update data on every single product in that order. But by making that trade-off, we have better scalability and faster queries. So relational databases were not designed for this use case. They were designed for having a single schema on a single database node that could support any query that you throw at it. This is what makes SQL so powerful right off the bat, is because we can perform any query we want on the database itself. With NoSQL databases, we're optimizing for making these decisions ourselves. So a NoSQL database doesn't enforce any schema at all usually, and it forces us to think about our query patterns and design our data model in a way that works for those specific query patterns. In order to accomplish that goal, NoSQL databases have a number of design decisions that differ from relational databases. First of all, NoSQL databases support a richer data model. So with a relational database, we're assuming all data is stored in a table, but in a NoSQL database, since we want data that's queried together to also be stored together, we can store what would have to be multiple tables in a relational database in one record. In MongoDB, for example, this is done by having a JSON object that can support nested arrays and objects within it. NoSQL databases, of course, also support horizontal scaling, so they have sharding built in natively, and it's really easy to shard a NoSQL database because of the way that data model is designed. And finally, NoSQL databases favor external functionality. So a lot of SQL databases support things like ACID transactions, schema validation, consistency guarantees, all built in, whereas NoSQL databases tend to require you to build that on top of the database so that you can do that in a way that is scalable and efficient for what you want to do with it. So for small scale applications, the trade-off between NoSQL and SQL databases is really just up to the developer's opinion of which they think is easier to work with. But for large scale applications, systems like MongoDB and Cassandra were specifically designed for supporting data sharded across a very large cluster of machines. If you enjoyed this video, you can find more content like this on interviewpen.com. We have tons of more in-depth system design and data structures and algorithms content for any skill level, along with a full coding environment and an AI teaching assistant. You can also join our Discord, where we're always available to answer any questions you might have. If you or a friend wants to master the fundamentals of software engineering, check us out at interviewpen.com.